In this class, we will consider some elementary calculus and its applications in physics, of course using Python. So let's see, let's look at the very basic things of calculus. Like you have, say, a graph, this x-axis and this y-axis, and this is y as a function of x, right? And say you have a graph like this. If you take any point here, it will have an x coordinate and a y coordinate. Now let us take 2 points nearby and we'll try to define the concept of that derivative. So here if you look at it, this is your delta y and this is your delta x, and the slope of the curve is delta y by delta x, right? And when we reduce the delta x, finally when delta x tends to 0, we call it as the derivative dy by dx, right? And all of you know how to find the derivative of a function, say y is equal to x square or y is equal to sin x, or those things. But suppose if the function is not given analytically in this form, suppose it is given as a table, something like this, say x and y, all the values are given, say for, so how do you calculate the derivative? And this will come in an experimental situation, like suppose, say we are doing an experiment of some object rolling on an inclined plane. So let us draw the picture, say something like this. Say we have an inclined plane here, and on that inclined plane, suppose we kept a small car or something, wheels, okay, and it will roll on the slope due to the effect of gravity. And here we are keeping a device, say something like an ultrasound echo device, that is capable of measuring this distance t. So that means we can keep on measuring this as it rolls. So what we will get is again this distance as a function of time, and say we make 2 measurements every second, so then we can tabulate, say at 0 this was the position, at 0.5 second, like that we can tabulate. So from that tabulated data, how we are going to calculate the velocity and acceleration. So we have to define all these things in a different way. So let us try to do that. Again, get our necessary tools, get the editor where you can start writing the code. So this table, for the time being, we have to cook up some data instead of the experimental value. Say what we need is the NumPy and Matplotlib modules for plotting and making the arrays. Both can be obtained by, say, import the statement, and the time axis, the time, so we call it as t is equal to, and I told you we take, say, 2 readings per second, so that means our delta t is 0.5. So now we create time array using the arange function, starting with 0 and go up to, say, 5 seconds, and every dt take the readings. And now our distance, say let's call it as y, that will, for the time being, we will make some value, like suppose say it is 2 t square. So this is quite arbitrary, but let us see how it looks like. So now we t versus y, if we plot, say mark the points as well, terminal, ls terminal. So we have a terminal here, and we'll run python diff.py. So we have this graph here. These are our experimental points. Say at 0.5 we have some value, and then 1 second, 0, 0.5, 1 second, 1.5. So these are the distances. So at for 0.5 seconds we just traveled something like 40 units. So from here, to calculate the velocity, suppose say velocity at this point, so velocity at this point is 0, and there will be some velocity at every point we have to calculate. But what we do is, for ease of calculation at the moment, we will try to calculate this midpoint here. That means this point, the velocity, we will take this velocity, this position minus this position divided by this time. That is our dy by dt, because velocity is the derivative of the position, right? So similarly, if you want to know the velocity at this portion, you take the distance traveled at 1.5 and distance traveled at 1, subtract that, so you just get this height difference divided by delta t, that is 0.5. So to plot that, we need to have one set of coordinates that is representing the midpoints. So let us make another array that is going to show the midpoints. That means we have to start dt by 2, that is 0.25, and we go only up to the last midpoint, and now you have to plot this also, like that, and plot these, say so dt. Okay, we cannot plot this like this because this will have only 19 elements. You will see that print length of t and length of dt. See the graph this time. Let us see. We can see this is 10 and 9 only, because the midpoints, if we have 10 total points, and these midpoints will be only 9. And now at each midpoint we should calculate the derivative. That means the dy by dx here. So n is equal to the length of the second. So we need to calculate n times, that is basically 9 times. So we calculate say dy dt, or we can call it as a velocity, right? Is equal to, say, keep an empty array there, and then inside a for loop, n times we are going to calculate that, and each what will be the result? Every step it would be see on the graph, say first it enters with say k is equal to 0, and there we have to write the y of k plus 1 minus y of k. This is our dy, right, and by dt. So this is the value, and this should be appended to our empty list. So we can just plot it and see now. So this is our v. So velocity. So this is how we calculate the velocity in this for loop every step. So let us have a look at the result. So you can see here, this is the velocity. It's a constant velocity. and position is going in this fashion. So here every midpoint we have calculated this dy by delta y by delta x, and as it goes, the curve goes steeper and steeper, the slope is also increasing. So here you can see this largest slope, and this is the largest point, largest velocity. And here we have done everything explicitly. We have taken each, say, k plus 1th point and subtracted the y coordinate of the, from that, the y coordinate of the k plus 1th point minus the kth point, right, divided by dt, we got the derivative. But actually you don't need to do all this extra work. NumPy gives some functions to calculate the derivatives. All we need to do is say dy is equal to gradient of y, and you can also say that dt is equal to gradient of t. In fact, it is not really needed because it's a constant gradient. We know dt is 0.5, but you can as well do it this way. And then what will be our v? V is equal to dy by dt. So let us plot it this way. So use the gradient function, and there's dt is not required, it is c, because it is not calculating for the midpoint, it calculates for every actual point. So you can see every position it says this is the velocity, right? But you can see, even though it managed to calculate for every point, but you can see here there is an error. So that's why we did not follow that method. But this, probably what we can do is we can exclude the last and first point from the calculations to get rid of this. And now if you do one more step, we should get the acceleration, right? So, and we can also make, say, finer measurements, like suppose we take every 0.1 second, then this is the case. Okay, now how do we get the acceleration? So v, and so again we have to take the gradient of v, right? That is a is equal to, let's just say dv is equal to gradient of v, and we just plot dv and this dt line is not really required, but let us put it. So dv by dt, let us put it here, and again plot it. So you can see that it is a horizontal line, and here you realize why we are taking that midpoint thing. You can see that the velocity, the last point was wrong, and here last 2 points are wrong. So even though the gradient function gives the gradient at every point, it's not really advisable. It gives some error at the endpoints. That is because of some of the assumptions it makes. But anyway, the idea was to just show you how you handle this differentiation numerically when you have experimental data. And now let's have a look at the reverse of it, that is integration. And integration, what is the need of doing it, integration this way, and what is the meaning of integration? Let's say we have some graph like this, that is y is equal to f of x, this x. Now when you integrate, what you are really doing, suppose you integrate this from here to here, that is say x1 to x2, right? That integral of f of x, x1 to x2, and what you are really doing is you are finding out this area under the curve. And that again, if you do it this way, small pieces, right? So x1, say take a very narrow strip somewhere like these and these, and say call these as a delta x, right? So this portion is the width is delta x, and here you will have say f of x, this y is equal to f of x this point, and this point will be y is equal to f of x plus delta x. So this area of this trapezoid you can calculate, and then you can add them together to get the enter the area of the curve. So that's how we do the differentiation. And the practical application, you can say, is how it appears numerically. Suppose you have a rain gauge kept somewhere, and it measures the amount of rain, say every half an hour, and from that, if you want to calculate the rainfall per for a whole day, you have to actually integrate it. That means what you are doing is the reading for or every half an hour you will be adding up together. So let us see how that can be done mathematically. So again, in this case, we will take another simple example. I'll not take an arbitrary curve. I'll take a curve that will allow us to cross check the results. Otherwise, whatever result we will get, we will not know whether it is accurate or not. So we will take a well-known curve that is a circle. So you have a quarter of a circle, say 0 to 1. So radius is 1, and this is x, and this is y. So here you have a arc, 1/4 of a circle. And what is the equation of a circle? That you know, x square plus y square is equal to r square. So y is equal to square root of r square. Here r is 1 in our case, 1 minus x square. So this equation we should integrate by making these small strips and calculating the area under the curve, like each strip, and we'll add it up. So let us write a program that does this process. So here we come and we start writing our radius is equal to 1, and our dx we are taking it as 0.1, and then again we have to make an array of x is equal to a range, say 0 into r plus dx and dx. So let us print this. So I should know what it is. So there is nothing to show. So I'm not plotting it, or you can even plot it actually. Say plot x. Oh, plotting you need y also, right? So let us make y also. What is our y? Y is equal to square root of 1 minus x square, right? So these are our points. So we are having, so let us plot the graph as well. See, this is our graph, and probably we can mark the points as well on the graph. That is something like this. And so here is our quarter of the circle, and you can see the points. X coordinate 0, then 0.1, 0.2, 0.3, we have this, and we will be making strips like this. Say from here one strip like this and another one. And now how do we calculate the area? Area is, suppose, say if you take, you can have a trapezoid in between. So suppose you take here these and these, and instead of the curve you just approximate it with a straight line, calculate that area. So we'll calculate that area. That will be this plus this by 2 into dx. So let us proceed towards that area calculation, and we need to know the length of the array, right? So how many are there? And there will be n, if there are n points, say there are 10 points, there will be only 9 trapezoids, right? Because one here, say 1 2 3 4 5 6 7 8, and 1 2 3 4. Okay, so here we have n is equal to, actually let us print n, it is not 10, it is okay, n is equal to total 11 points we have defined, so there are in between 10 trapezoids. Okay, so how do we calculate the area of this trapezoid? So let us proceed with that calculation. Like, say, assume the total area, start with 0, then we start a loop, for loop, okay, in a range that is n minus 1. I told you that is, if there are n points, there is only n minus 1 trapezoid. Area of each trapezoid will be y of k plus y of k plus 1, the y coordinate of two adjacent points, divided by 2 into the dx. And this each area, let us add to get the total area, so dat. Okay. Now here we print our results a. And what is expected result? If you have a circle with radius r, area is equal to pi r square, so this r is 1, that means pi, so this will be pi by 4, right? Area of quarter of the circle, unit radius is pi by 4. So let us try to put pi by 4 also here, so that we will compare our result with the actual pi. So you can see we get something like this, but actual pi by 4 is 785. That means our results are not accurate, because you can see each curve, our approximation is not really good. So how do you improve the accuracy? You just reduce dx, finer division. Now 7853, so up to 4 decimal places it is tiling. So if you can keep on increasing this number, reducing dx, and get better value. But again, here we need not do it like this. This is just to show you what is the technique involved and what is the meaning of it. But again, SciPy gives you, that is the Python, there is a Python module that is called scipy.integrate. So let us get that. There is a package called SciPy, and in that we need to get the import a module called integrate. So from SciPy, import integrate. SciPy import integrate, and what then we can say print integrate module dot code, that is the function. But where is the function? So this will, you have to give the function and the two limits, but we have not given the function, so we have to define that function now. Say f of x, like you know how to write a Python function, right? So it returns, what it supposed to return? Square root of 1 minus x square, right? That's all it should return. And no more graph, anything. So this, let us see what it gives. It gives this value, and this is the estimated error, that is small. So let us, so it's returning a tuple with the actual result and the errors. So we need to see only the first element and compare that with 5 by 4. Run it again. You see these are the result, they are tallying in 12 digits. So this integration is much better than what we do, but we did it just to understand the process. So now we have some idea about how to handle the calculus using the numbers, arrays, instead of using analytical functions. So we are doing them numerically, and our next step would be to use these differential equations for some applications in physics. So that we'll leave it for the next class.